Okay, we're getting into some more complicated examples here. This x cubed minus 3x squared plus 3x graph, this is one where you would probably just do table of values. You get some easy points here like 0, 1, 2. Just get the general shape of it because the boundary is between 0 and 2, so you only have to graph it in between there, and a general idea is pretty good. So if I plug 0 in, I get 0. I'll use green again. If I plug a 1 in, we get 1. Minus 3 is negative 2, plus 3 is 1. And if I plug a 2 in, lo and behold, I think I get 2. So it looks like a straight line, but it actually does some wonky curve like this. I'm going to, over draw it just so it looks really, really good. Like so. But usually in your questions, you'll either have the image or it'll be a pretty basic graph. The graph y equals x now, we can draw that. And maybe I'll change colors on this one because it's a little bit more through and through. So there it is. And you can see the area is bound by the curve. There's two separate boundaries. So on a question like this, put a big fat star here, add up the areas. So if you have two graphs that cross and create more than one area, you could have 2, 3, 4, doesn't matter how many areas. You're just going to add them up, and you might have to switch which one's higher. Like your f of x can change to your g of x and vice versa. So if we look at the two separate things here, in this first section here, I would say it's f of x is on top and the g of x is on the bottom. And same thing here, we'd have f of x here and g of x here, just like so. So you can see how our green line went from g of x originally on the right hand side to f of x, and it doesn't matter. You can call them whatever and look at the different areas. Now this is a perfect question to show you that you could do it in terms of y as well, going the other way, but because it's y equals and y equals, and they've given you the domain in between 0 and 2 already, because the domain is bound that way, I know it should be in terms of x, f of x, g of x, whatever you want to call it. Okay, so that's how I sometimes figure out which way is the best way to do it is based on the domain. So here we go. Area equals. We'll just look at the first one here, the x cubed, the smaller, the lower part of the graph. So our boundary there is from 1 to 0. Our x cubed graph is our f of x. So we'll write that out first. Minus g of x, so minus x. And that's d of x, right? So I'll put d of x. Plus the integral from 2 to 1. And you'll notice that your integrals always are going up. So 0, 1, 1, 2. And if we had another one, it would be from 2 to 3, 3 to 4, and so on. Or 2 to 5, whatever goes, okay? Now we got to flip this around because now it's x minus our cubic graph. So this is, I'm just going to put this in because I'm running out of room here. So x cubed plus 3x squared. 3x squared minus 3x. And look at me squishing that in there. That's great. D of x. All right. We'll simplify and then take the integral. So we've got the integral 1 to 0, x cubed minus 3x squared plus 2x. And then d of x plus the integral 2 to 1. X minus 3x is negative 2x minus x cubed. And then plus 3x squared, d of x. Now we've simplified it, we can go and do the integral. Area equals x to the 4 over 4 minus x cubed plus x squared from 1 to 0. Now, where'd those other numbers go? They obviously simplified out, right? Because if you get 3 over 3, it's gone. 2 over 2 is gone. Plus negative x squared. Now, I guess I should put this one in brackets because we're going to have the whole thing added. Minus x to the 4 over 4. And then plus x cubed from 2 to 1. Now, you can see there's some involvement going on here. We'll try and squeeze this answer in down here. The first one here, we go plug all this in. The first part doesn't really matter. You just plug the 1 in, right? Quarter, minus 1, plus 1. So you got a quarter. And then the 0 is not going to affect it. But plus this right-hand side, that's going to have some numbers involved. So go calculate that out. I think you get negative 4 plus 8 minus 4. So that's gone. And then minus a negative a quarter plus 1 minus 1. So you end up with a quarter plus a quarter in the end, which works out to be a half. Oops, maybe make that a little bit neater. Squeeze in 1/2 units squared. So that curved area, the two curved areas, added together is a quarter and then another quarter, which would give you a half. So some engineer would tell you that's how you calculate it out. Last one for this video. We're just going to do these two because then I think that's enough to get you started. And then there's always the idea of a system of equations. So maybe when you get in around question 15 or so, I think question 15 might be the first one you come across in the assignments. Let me know and I'll maybe put up another example, but this will get you started. So let's graph this one. Y equals x real quick, like so. Y equals negative x real quick, like so. And we got y equals 2x minus 3, so I'll go and graph the minus 3 up 2 over 1. And then I believe all the way up at 3. Right, we go up 2 over 1, up 2 over 1, yeah. So like so. So this graph is like so. Now, if you didn't know where they intersected, and we do at the point 3, 3, you'd have to find that. Same with down here. This is at 1, negative 1, because these are where your boundaries are created, 0, 0. Because now you're going to create your own. So in the last example we had, it was pretty obvious where they intersected. Now you can see in this question where this change is right there, right along that line. Okay? I'm going to draw it straight there. So you've got an area here that you can find, and I'll switch it over. You got an area here that you can find. You're going to add those two up. Now, they're both in terms of y, but on the first part, if you look, here would be my f, here would be my g. And then after we get on the left side of that red line, this line here is still my f, but now my g line switches to the negative x line. So you got to really follow along. Again, on the right-hand side, the higher one is right there. The lower one is this g. On the left side of the red line, your f stays the same line, but your g switches. So your integral is going to be like so, and you got to watch these boundaries, and that's why they're so important. Because your boundaries are x values in this one. So let's go do the left side first, I guess. So from 1 to 0 is that what we're looking for. Our f of x is just y equals x. So x minus a minus x is plus x d of x. Plus the area bounded by from 3 to 1 is the x values that it's bound by. And then that is going to be x minus 2x plus 3. If I throw in the negative. just like so. Now, it wouldn't matter if you did what I did in the reverse order, like if you did the 3 to 1 plus the 1 to 0, as long as your boundary points are in order. So if you flip those around, you went 3 to 1, 1 to 0, 0 to -2, -2 to 5. As long as it's in order, that's fine. Okay, let's keep going. Area equals 2x, right? This is just 2x. So the integral of that one is just x squared from 1 to 0 plus, this here simplifies to be -x plus 3. So that'll be, put this in brackets, I guess, -x squared over 2 plus 3x, bounded from 3 to 1. Now let's walk this one out. So we got 1. Here's the first part. Plus, keep all this in brackets, -9/2 plus 9 minus -1/2 plus 3. So there it is. I've plugged in that 3. I've plugged in the 1. And that's what it looks like. So we go and we simplify all that out, and we get a magical, wonderful 3 units squared. When you go and solve that, you'll see that the answer comes out to be 3. So the area of that triangle on the left plus the area of the triangle on the right, that's all shaded in yellow, works out to be 3 units squared. So again, let me know when you get to about question 15 or so, and I'll maybe throw out 2 more examples for you. Maybe I'll just do question 15 and question 17 because they're pretty cool questions to see done. Okay.